Okay, we have closed the mass balance and we were going to go to model fit now, but we actually omitted a step. Let's go back to mass balance because we can. And this is where we were last. We have completed this table and we didn't look at the data status, measured, excluded, everything. We didn't look at the standard deviation table. So these values are all 5. We can review them and we calculated. There's nothing close to 5, but it gives us what the standard, so with this 5%, it tells us what the standard deviation will be. My apologies, these are percentages. Once we have enough data, we can edit that. We don't, so let's just not do it. Let's go to balance. Working from left to right, we can say all minerals must add up to 100%. All assay data must add up to 100%. So we're going to click those. We can weigh low-grade things like gold. We can use the least squared method. We can constrain values. We can do all sorts of things. See, this will be nice if we say, well, the goethite can only be 1/3 of the total iron content, as an example. We have an unsized model, but we can also choose to do size by assay if we have the data. The balance type, we can do our mass balance on assays only, on minerals only, or on both. Let's do it on both just for fun. And then there's a magical calculate button. Okay, so I have now said all things must add up to 100%. Let's press the button and see what the model spits out for us. It's calculating. It's already on round 300 and counting. Okay, and it's not really converging to anything. It's not getting to our tolerance either. Isn't that interesting? It's just not working. And it went to 1,000 calculations and then said, well, this is my end result. Actually, there I had a better result. So that's interesting, isn't it? Let's have a look. For the first sample we pulled off, we measured after mineral conversion that there's 50% quartz, and this one says, no, there's only 31% quartz. And there's 46% magnetite. No, there's 66% magnetite. Already I'm not very happy with this method. However, if I switch off these two options and I press calculate, zip, it just converged very quickly. And if we now look at this exact same data, quartz 50%, 46%. Magnetite 46.5, 47%. This is already looking a lot better. So the point is, you have to select the right method to do your mass balancing. Let's go to a large stream like tails, 71.5, 71.3. We can obviously use different methods like non-negative least squares, the one that worked well the last time. I'm going to accept what we have now, but the point is, please play around with the methods to make the mass balance suit your data and match your data better. I'm going to save this to the flow sheet, and we now have our mass balance completed. I'm going to save the process. By the way, I also have a little thing here called autosave in 15-minute intervals, and it's now switched off. I leave it switched on because computer reasons. Let's go to model fit. This is going to be short and quick, and it says select the concentrate streams. Not all the streams? No, just the concentrate streams. Fine, I'll do that. So these are the concentrate streams in my model. Is that it? Is all I need to do? Yes, let's apply that. So now it knows exactly what's happening. So now I get presented with this screen, and if you've studied metallurgy, you know that there are various kinds of models you can fit to flotation data. You can have one component, in other words, floating. You can have two components, fast floating, slow floating. You can have three components, fast floating, slow floating, non-floating, and a rectangular distribution. And you can do that for these type of batch measurements. You can do it for continuous or samples from a continuous operation. Let's take one mineral and go through all these options because it's fun. So you see that these are yellow and that flotation time is blank, and that I have cumulative selected. In other words, this is cumulative time. I'm going to switch this off, and did you see all the numbers change? That's just the internal calculations, but I know that this was 1 minute in each case. However, if I now switch on cumulative again, it will say that it went for 8 minutes. Pretty cool. Now, I can do a model for calcium. It's not useful, but we can. However, we want to, of course, do a model for a mineral. So let's go to magnetite. All I did was select magnetite. I can select hematite. Magnetite, and I press model fit. So this is a one component model for magnetite, and it says that, well, the model doesn't really fit very well. Okay. And yes, you know exactly where I'm heading with this. If I press magnetite, still selected, model fit for a two component one, I didn't really get any better, did it? Let's do a three component lab model. Still didn't get much better. A rectangular distribution? Well, that didn't really help, did it? So now that becomes very interesting. I'm going to switch off cumulative. I'm going to go back and do this again. I'm going to go two component. The thing is, it just does not predict well. And it says, if we look at the bottom here, that using a three component model, that it floats really fast, and that there's no slow floating or non-floating components for the magnetite hematite blend. You know what? I don't like that. So the initial, it should float slower. So let's just have a look at quartz. I'm just going to look at the three component one. Well, this looks a bit better. Doesn't quite fit there, but it's already a bit better. The rectangular. No, that doesn't really do it. Okay. So let's stick with three component. And I think this is good enough. So I'm going to say accept this flotation model for quartz. And what does it say? It says quartz floats fast. There are no slow or non-floating components for quartz. For this data and for the way we've treated the data so far. Okay, lots of caveats. Let's go back to magnetite for three component lab. I don't like this data. Why don't we just change some of these values? I'm going to say the maximum you can do with this is 0.7 fit a model. And now it has fitted 0.7. It still doesn't quite work. How about 0.5? No, it doesn't want to do anything. It says no, you got to float these things fast. So let's give it a 0.2. Even when it's 0.2, it still wants to fit this curve. So now we're sort of stuck. Our two most prevalent minerals, quartz worked well, hematite, magnetite, goethite did not work well. I think we need to go back and look at our data. And this is the point. Now you've got to go play with, one of the other methods, perhaps not have everything add up to 100%, maybe have it add up, those type of things. I'm happy with quartz, so let's come back to this one. Let's have a look at calcite. Why are these values negative? Well, perhaps because there's a problem with the data. And as you can see, things are just not working the way they should. I chose this example for a reason. Things are not looking really good. Let's do talc. No, still doesn't work. Pyrite? Can we do pyrite? No, also not quite. So the thing is, do we have confidence in our data, or is it just the model fitting that's the issue? Well, I can tell you that it's the way we treated the data. I'm going to discard and close all of this. We're going to go back to mass balancing. I'm going to treat the data differently. Our measurement data, we are going to change. We are going to get rid, firstly, of our estimated values. We're going to get rid manually of the minerals for these estimated values. And we're going to fix these minerals, because I'm not happy with these minerals. So let's go element to mineral conversion using HSC Geo. Let's go through this again. Select all of those, select all the minerals, calculate, and we're back where we started. Remember, 105, chemical total, negative dolomite. And let's go back to the rules. Remove dolomite. We know by now remove hematite and goethite, and calculate. And we're now at 100%. Everything is magnetite, everything else is mostly quartz, and there's a little bit of other things as well. I'm going to update and close. And we're going to go to the mass balance bit. So we're just going to go estimate the missing values. Now it calculates all of these values, or we can say clear it. Doesn't really matter. Let's go to the balancing bit. I don't want things to add up to 100%. I want to calculate the balance. And did you notice earlier on in the video, these values did not balance properly, but now it does. And look at my conversion, e to the minus 5. We now have with a tolerance level of e to the minus 3. So now we get an answer that makes a lot more sense. So what did I do differently? These do not add up to 100%. I didn't constrain that. And the first thing we did was, of course, we did not predict other values. Save and close. Save the process. Go back to model fit, and let's have a look. We now know the drill, so let's do this quickly. These are our concentrate streams. Let's go to magnetite. We'll use a 3-component lab model fit. Now, isn't that interesting? Now I get something that fits quite well. My grade recovery fits well. And look at these guesses. 0.7 is fast floating. There's nothing that's slow floating, and some of the magnetite, hematite doesn't float at all. And the kinetics for fast floating is 27% per minute, and for slow floating is nothing. I like this. So I'm going to accept this to the list. Let's do the next mineral. There is no hematite, so it's empty. Let's have a look at quartz. 3-component model. Looks a bit better, doesn't it? Everything works well, except this curve, this kinetics. And let's just have a look. Most of the silica is fast floating. There's some slow floating and there's some non-floating. And this one says that per minute, 100%, 118% can float in the first minute. For the slow floating ones, it's 30% per minute. So it takes 3 minutes for the slow floating ones to eventually get to the launder. Yes, I like that. So this is quartz, that's in. Let's do calcite, model fit. It looks good. What's going on with our data? This is the source data that does this. So this data point here, there's something wrong there, because this data point here should be over here somewhere. Okay. We're dealing today just with a simple computer program. You need to ensure the data fits well, but the point is you have tools here that can help you. I don't like this model fit for dolomite because it says dolomite floats too fast. Let's have a look at its values. 100. No, clearly not. But the point is, did we have dolomite in here? We did not. So let's not get bogged down with dolomite. Let's go to talc. Talc fits properly, except to this. So we'll look at pyrite. Pyrite fits okay. It's not perfect. It's slightly slower and then it picks up again. But as a fitted curve, and since there's so little pyrite in, it's okay. And also, in 8 minutes, most of the pyrite reports to the tails, to the concentrate, reverse flotation, which means it doesn't go to your final product that you're going to sell. So for pyrite, I accept this model. Go for it. There's no goethite data, so this dolomite data, could have made a mistake and included it, but we're not going to. I'm going to save and close this. We are done. We have the kinetics, which are now off the screen, so we can do better than that. So we're going to go back to Tools, Model Fit. Did we just lose all the work we did? That's the whole point. So here's the work we did. And there's this fancy little thing called copy. So I'm going to copy this. I'm going to paste it in Excel so we don't lose this again or have to open this window again. Blank workbook, that'll do. Paste. Okay, I'm going to put that at the bottom of the screen there. We are finished with this model, so we can save this and we can close it. In the next video, we're going to look at a full-size flotation plant using the kinetic data that we calculated from the test work data for the minerals magnetite, quartz, calcite, talc, and pyrite. Let's do it.